Welcome to AI Journal Club, the digital pathology podcast segment where we take a closer look at the research shaping AI in pathology. This episode is one of our AI-powered summaries series, AI-generated deep dive into a paper worth your attention. It's curated from our weekly DigiPath Digest live stream that I run every Friday morning. I'm Dr. Alex Żuraw, and this is your shortcut to stay current. Let's dive into it.
What if the greatest medical AI ever built doesn't actually save lives by being perfectly right, but, by knowing exactly when it is completely confused?
It's a pretty wild concept when you really think about it.
It really is. Well, welcome to the Digital Pathology Podcast, Trailblazers. Today we're doing a journal club-style deep dive into a really massive new paper recently published in NPJ Digital Medicine.
Yeah, and it's an incredibly timely piece of research. The paper is titled High-Sensitivity Pan-Cancer AI Assessment of Lymph Node Metastasis via Uncertain Quantification.
Which is a mouthful, I know.
Right, it is. But it's this huge multi-center collaborative effort led by authors Xiaodong Wang, Ying Chen, Xiaolong Liu, and corresponding author Guanzhen Yu from Stadion University, along with a bunch of other major institutions.
And the scale of what they've accomplished here is staggering. But our mission today isn't just to throw big numbers at you. We are going to unpack a new AI platform they developed called UPATHLN. Because this system does something incredibly rare in the world of machine learning, it actually weaponizes its own doubt.
Yeah, which is fascinating.
But to really appreciate why that is such a fundamental shift in healthcare, we first have to understand the sheer, crushing operational reality of a modern pathology lab.
Crushing is definitely the right word. I mean, if you walk into any major hospital's pathology department right now, you will see a system that is just completely overwhelmed by volume.
Because global cancer rates are rising, right?
Yes, and with almost every surgical tumor resection, the surgeon also removes the surrounding lymph nodes.
Right, because the lymph nodes are basically the anatomical checkpoints. If a primary tumor, say, in the breast or the colon is going to metastasize and spread through the body, it almost always travels through the lymphatic system first.
Precisely. So the pathologist has to look at these nodes under a microscope to find out if the cancer has breached the perimeter. And that dictates everything.
Like the prognostic staging and treatment plans.
Exactly. It determines whether the patient needs aggressive systemic chemotherapy or if they can safely go home. But searching for a microscopic cluster of metastatic cells in a sea of millions of healthy lymph node cells, it's a brutal, fatiguing task. It's the ultimate diagnostic bottleneck.
Naturally, the field has turned to deep learning AI to automate this screening. I mean, we've all seen dozens of headlines about AI spotting cancer.
Oh, absolutely.
But the paper points out a massive operational flaw with the tools currently on the market. They suffer from what's called the silo problem.
Right, because historically, developers have built these highly specific, narrow models. So you have an AI trained exclusively to find breast cancer in lymph nodes.
Okay.
Then you have a totally separate software suite for lung cancer and another one for melanoma.
So you just have all these different programs running at once.
Exactly. And for a high-throughput pathology lab, deploying and managing a dozen fragmented, disparate algorithms is an IT and operational nightmare. They desperately need a unified pan-cancer standard, one AI that can evaluate any lymph node from any organ.
But building a single AI that can look at any cancer brings up a terrifying biological reality, which is the concept of the long tail.
Yeah, the long tail is a huge hurdle. Tumor heterogeneity is just vast and chaotic. Yes, there are common metastatic patterns that are very easy to train an algorithm to spot, but biology is messy.
Right.
There is this long tail of diverse, highly atypical, rare cellular variants. You have strange morphologies, bizarre growth patterns, cells that don't look like classic cancer at all.
And in machine learning, we call this out-of-distribution data, right?
Exactly. It is data that falls completely outside the normal bell curve of what the AI saw during its training phase.
And standard deep learning models handle out-of-distribution data incredibly poorly.
Yeah.
They don't just politely say, hey, I don't know what this is. They suffer from what the authors call overconfident errors.
Which happens because of how standard neural networks are structured mathematically.
Mm-hmm.
Most classifiers use an output function called softmax.
Softmax, okay. How does that actually work?
Well, Softmax forces the AI to divide its certainty across the categories it already knows, and it has to add up to exactly 100%.
Oh, I see.
So if an AI only knows how to recognize normal tissue and classic tumor tissue, and you show it a bizarre, rare variant it has never seen, it doesn't have an other category. It literally forces a guess.
So it might misclassify that rare cancer as healthy tissue.
Right. And because of the math, it'll output that wrong prediction with 99% certainty.
Okay, let's unpack this for a second, because usually in tech, we celebrate a highly confident AI. But in a safety-critical field like oncology, that is terrifying.
It really is.
It's like a self-driving car that handles highways perfectly, but confidently accelerates into a lake because it has never been trained on what a boat ramp looks like.
That's a great way to put it.
A 99% accuracy rate on a spec sheet is entirely hollow if that remaining 1% is a highly confident missed micrometastasis that costs a patient their life.
Which brings us to the actual architecture of UPATHLN. The team at Zidane University recognized that to build a pan-cancer model, they couldn't just throw more images at a standard classifier.
Right, that wouldn't fix the core issue.
Exactly. They had to architecturally prevent those overconfident errors. They had to build a safety net.
Let's break down how UPATHLN actually works from the ground up. Because before the AI even starts looking for cancer, it has to find the actual lymph node on the digital slide.
And a surgical slide is not a clean, neat circle of tissue. It is cluttered with fat, connective tissue, and muscle.
So they built a highly robust two-stage preparation pipeline to handle that exact messiness.
Right. First, they use an object detection model called YOLO-VATES. YOLO stands for You Only Look Once.
Catchy name.
Yeah, it is. And it's incredibly fast at scanning a massive whole slide image and drawing tight bounding boxes around potential lymph nodes. It operates with a 0.994 recall rate.
Meaning it almost never misses a node.
Exactly. Then it hands that localized region over to a second model, a segmentation network called NUNet, which essentially acts like a digital scalpel.
Wow, a digital scalpel. So what is it cutting away?
The NUNet traces the exact borders of the lymph node, digitally cutting away the extraneous adipose or fat tissue.
Oh, that makes sense.
This is crucial because fat and muscle introduce visual noise that distracts the core diagnostic AI and wastes immense computing power. The paper notes it achieved a DICE score of 0.934.
Wait, I want to pause on that term, DICE score. What does a 0.934 actually mean in physical terms?
So a DICE score measures spatial overlap. If a human expert carefully traced the exact border of the lymph node with a digital pen, and AI did the same thing independently, a score of 0.934 means their tracings overlapped with 93.4% pixel-perfect accuracy.
Oh, wow. So it's practically identical.
Yeah, it's a phenomenal level of precision for preparing the tissue.
Okay, so the tissue is perfectly prepped, the noise is stripped away, and now it moves to the brains of the operation. The team utilized something called the UNI Pathology Foundation model.
Right.
And this isn't just a basic image scanner. It's a massive vision transformer pre-trained on over 100,000 whole slide images.
And the shift from older convolutional neural networks to vision transformers is really significant here. Transformers are uniquely good at looking at global context.
Because it was pre-trained on such a massive, diverse data set.
Exactly. So it already understands the fundamental underlying language of human tissue before it's even asked to look for cancer.
But to make it hypersensitive to metastasis, the authors designed a multi-scale cross-attention framework.
Right.
If you think about how a human pathologist physically operates, they don't just stare through the microscope lens at one single static magnification. They zoom out to a 4x magnification to look at the architectural pattern.
They're asking, are the cellular structures forming normal glands, or is the architecture collapsing?
Exactly. Then they zoom way in to a 10x or 20x magnification to look at the nuclear details of individual cells.
They need to see the forest and the trees simultaneously.
Yeah.
And this AI mirrors that biological workflow. It extracts features from both 4x and 10x magnifications.
Oh, very cool.
But it doesn't just awkwardly lay them on top of each other. The cross-attention mechanism allows the AI to dynamically weigh the importance of the zoomed-out architecture against the zoomed-in cellular anomalies.
So it's fusing them into a single, highly informed diagnostic prediction.
Exactly.
Wait, hold on. If the model is already this structurally sophisticated, if it has a vision transformer and cross-attention fusing different magnifications, Why do they need to build a second system just to guess if it's wrong?
It's a fair question.
Like, why not just train this main classifier to output a low confidence score when it gets confused?
What's fascinating here is that is the exact crux of the engineering challenge. If you try to force a primary diagnostic classifier to simultaneously calculate its own uncertainty, it creates a computational nightmare.
Really? How so?
Well, in machine learning, trying to optimize a model for two totally different goals often causes the mathematical gradients to conflict. It can actually destabilize the AI's primary task of finding the cancer.
Oh, so it gets worse at its actual job.
Exactly. The other traditional option is an ensemble approach. That means running the image through 5 different independent models and seeing if they agree.
Right.
But doing that for massive gigapixel pathology slides would require absurd, completely unaffordable amounts of computing power.
So they decoupled it.
Yes. They froze the main diagnostic AI so its primary function wouldn't be disturbed at all. Then they built an independent bypass module that runs entirely in parallel.
And this is the uncertainty estimation module.
Correct. It takes the features extracted by the main network and essentially calculates the predicted loss.
And predicted loss is essentially a mathematical measure of the AI's internal struggle, right?
That's a great way to think of it, yeah. When the AI is looking at a standard tumor, it understands the calculations align perfectly, and the predicted loss is low.
Makes sense.
But when the features start looking weird, when it encounters that out-of-distribution long-tail data we talked about, the internal calculations don't fit the pre-trained patterns.
So the loss metric spikes.
Exactly. When that spike happens, this parallel module explicitly flags the region as high uncertainty, or HU.
Yeah.
And because it's a lightweight parallel bypass, it doesn't slow down the overall inference speed of the system at all.
Wow. So what does this all mean for the user? Instead of the AI acting like an arrogant doctor who refuses to admit they haven't seen a rare disease before, it is acting like a brilliant medical resident.
I like that analogy.
Right. The resident confidently and accurately handles 90% of the routine cases on their own. But the absolute second something that's mathematically weird, a strange cell shape, a blurry scan, an odd pigment, they immediately pull the fire alarm to page the attending physician.
It was a literal, hard-coded failsafe.
And the researchers didn't just bolt this failsafe on at the end, did they?
No, not at all. They used this exact uncertainty mechanism to actually train the AI from the very beginning using an active learning strategy.
Let's talk about the training because the scale of the validation here is wild. Typically, training an AI like this requires human pathologists to manually annotate every single pixel of thousands of slides.
Yeah, which causes massive burnout. It literally takes years of exhausting manual labor.
Right.
Instead, the team used uncertainty-driven active learning. They had the AI scan a massive batch of unannotated slides. The system then summarized the microscopic tile-level uncertainty into a broad slide-level ambiguity score.
Meaning the AI essentially raised its hand and said, hey, out of these 10,000 slides, these are the top 100 that confuse me the absolute most.
Exactly. And the human pathologist only had to spend their time reviewing and correcting those specific, highly ambiguous slides to optimize the model.
That's brilliant. It's like a student only bringing the hardest calculus problems to the professor instead of asking them to grade basic addition homework.
It is incredibly efficient. Over 5 iterations of this human-in-the-loop active learning, the model's performance just skyrocketed.
And the data set they used for validation was huge.
Massive. They validated the system on 26,229 lymph nodes from 14 distinct primary organs. On their internal validation, they hit an area under the curve, or AUC, of 0.986.
Which is amazing. For context, trailblazers, an AUC of 1.0 is absolute perfection, and 0.5 is basically a random coin flip. So 0.986 is stellar.
Absolutely. But the climax of the data, the moment in the paper where you really feel the clinical weight of what they built, is when they unleashed the system on an independent, multi-center test cohort of over 16,000 lymph nodes.
Yeah, they ran a fascinating baseline test to prove their concept. First, they turned off the uncertainty module. They let the standalone classifier try to find the cancer entirely on its own.
And it did great, but it wasn't perfect. The standalone classifier missed 60 lymph node metastases.
Let's just pause right there and feel the weight of that. 60 false negatives.
It's sobering.
In the real world, that is 60 patients who might be sent home with a clean staging report, told their cancer hasn't spread, while microscopic metastasis is silently moving through their lymphatic system.
But then, the researchers looked at what happened when the parallel uncertainty estimation module was running. That fail-safe mechanism successfully intercepted and flagged all 60 of those initially missed instances.
Here's where it gets really interesting. Wait, so it effectively neutralized its own blind spots?
Completely. Every single false negative that the main AI missed was caught by the parallel module.
Unbelievable.
The mathematical anomaly caused a spike in predicted loss, and the system flagged those specific regions as high uncertainty, routing them for mandatory review by a human pathologist.
It achieved a 100% conditional sensitivity, not by being perfectly accurate, but by being perfectly self-aware.
Yes, exactly.
It is like having an editor who might occasionally misread a highly technical word, but who always highlights the exact paragraph where they felt their eyes glaze over, forcing the lead author to double-check it.
The system literally guarantees that its own algorithmic limitations do not translate into clinical diagnostic errors.
And the authors refer to this as the rescue effect, right?
Yes. But they wanted to see if that rescue effect held up under extreme pressure. So they pushed the UPATHLN system to its absolute breaking point with an ultimate stress test.
The unseen cohort. They tested the model on 7 cancer types that were strictly withheld during the training phase.
We were talking about lymph nodes from thyroid cancer, pancreas, bile duct, kidney, prostate, penis, and itis.
The model had literally never seen what metastasis from these specific organs looks like.
And yet, the failsafe worked flawlessly. Even though the primary classifier was flying blind, the uncertainty module caught the anomalies. 0 misdiagnoses across the entire unseen cohort.
But how does it actually react when it's flying blind? You mentioned penile cancer earlier. If it hasn't seen it, what does the output look like?
Well, penile cancer metastasis has incredibly complex, atypical morphology. It looks profoundly different under a microscope compared to standard breast or lung cancer. For the other unseen cancers, the high uncertainty rates hovered around a manageable 5 to 10%. But when the system encountered penile cancer, the high uncertainty flag spiked to 30.2%, and the false positive rate jumped to 20%.
Which on paper sounds like a massive drop in performance. I mean, isn't that a failure of the model?
No, actually, the authors point out this is a brilliant adaptive behavior. The system recognized that it was mathematically out of its depth, and it dynamically prioritized diagnostic safety over efficiency.
Oh, so it essentially told the lab, I don't know what this biological pattern is, so I'm going to flag a third of these slides. Human, you need to step in.
Exactly. It is the ultimate manifestation of the Hippocratic Oath applied to machine learning. First, do no harm. When the model lacks data, it defaults to extreme caution.
And it wasn't just flagging weird cancer, it was flagging weird normal stuff too. Look at what happened with the lung cancer nodes. The high uncertainty rate there hit 32.6%.
Yeah, that was a huge finding.
When the pathologists dug into the audit to figure out why the AI was freaking out, they realized it was constantly flagging anthracotic pigment.
Right. And anthracotic pigment is essentially carbon or soot that accumulates in the lungs and draining lymph nodes of people who breathe polluted air or smoke heavy tobacco.
Wow.
Under a microscope, it looks like dark, ominous, granular material.
So it's acting like a rookie detective who finds a bizarre, muddy footprint at a crime scene. They don't know if it's the killer's shoe or just the gardener's boot, but they secure the scene and call the chief of police anyway.
Exactly. And we can actually see this behavior mapped out mathematically.
Right.
The researchers used TSNE dimensionality reduction to visualize how the AI groups these features.
Explain TSNE for us, because the visualizations in the paper are striking.
Sure. Think of the AI's brain as a complex 100-dimensional map of tumor features. It's something impossible for a human to visualize.
Yeah.
TSNE is a mathematical technique that takes that 100-dimensional map and squishes it down flat onto a 2D piece of paper so we can physically see the boundaries the AI has drawn between healthy tissue, cancer, and the unknown.
And in the TSNE visual plots, the high uncertainty regions are clustered perfectly right at the boundary between tumor and normal tissue.
Exactly. The system explicitly grouped tissue bleeding, dense connective tissue, and poor quality blurry image areas right into the uncertainty pile.
It fundamentally knows what it doesn't know. But that raises an operational question. If this AI is constantly raising its hand and asking for help every time it sees soot or a blurry scan, does it actually save the hospital anytime?
We definitely have to look at the return on investment for the pathologists.
Right.
The efficiency metrics are highly compelling. To quantify the actual workload reduction, the authors calculated the review burden rate on negative cases, or the RBRN.
And this metric accounts for every single time the AI generated a false positive or threw a high uncertainty flag on a perfectly healthy node. The RBRN was 26.8%. Let's do the math on that. That means a staggering 73.2% of all negative lymph nodes were safely, confidently excluded from manual review.
Think about the physical hours saved. Pathologists are no longer spending half their day grinding through thousands upon thousands of obvious, routine negative slides.
And if we step back and look at the broader impact, what do they do with all that reclaimed time? The paper argues that this is the gateway to practicing true precision oncology.
If we connect this to the bigger picture, historically, because of brutal time constraints, pathologists provide what is called crude PN staging.
Meaning?
They're essentially just counting how many nodes have cancer in them. 1 positive node, 2 positive nodes. But with 70% of the negative workload automated away by UPATHLN, pathologists are liberated to perform multidimensional analysis on the positive nodes.
Like calculating the exact lymph node ratio, or LNR.
Yes, or mapping the spatial distribution of the metastatic cells within the node itself. This is critical.
So they can see if the cancer cells are clustered tightly together or dispersed widely throughout the tissue.
Right. And how are they interacting physically with the patient's immune cells in the microenvironment? Recent biological evidence shows that these granular spatial features are deeply linked to patient survival rates and the mechanisms of immune escape.
So we are shifting the role of AI.
No.
It is moving from being just a basic automated slide reader to being the ultimate triage master.
Yeah, exactly.
It clears out the mundane brush so that the trailblazers listening to this right now can actually practice precision oncology. They can do the high-value, complex biological interpretation that is practically impossible to do manually at scale.
It elevates the pathologist from a repetitive visual screener to a true diagnostic strategist. And it definitively proves that explicitly modeling uncertainty, literally engineering an algorithm to doubt itself, is the key to unlocking reliable, safe pan-cancer diagnostics.
It is an absolutely stunning piece of work. We highly recommend you pull the full paper by Wang and Yu in NPJ Digital Medicine and look at those TSNE visualizations yourself to really grasp how the AI categorizes the unknown. Thank you for joining us on this Digital Pathology Podcast deep dive to explore this paradigm-shifting research.
It's been a really fascinating exploration of where the field is heading.
Before we go, I want to leave you with a final lingering question to mull over. If explicitly modeling uncertainty, literally hard-coding doubt into an algorithm unlocked this incredible level of 100% conditional sensitivity in pan-cancer pathology, what does this mean for the rest of medicine? We started this conversation talking about the comfort of a confident diagnosis, the demand for crisp, binary answers from our machines. But maybe we've been asking the wrong thing of artificial intelligence all along. Imagine a future healthcare system where the ultimate measure of a clinical AI isn't its raw predictive confidence, but the precise, calculated calibration of its own humility.
That's it for this AI Journal Club episode. If you want more like this, make sure you're subscribed to the Digital Pathology Podcast. And come join us for the DigiPath Digest, our weekly live session. During these live streams, you can vote which paper becomes an AI deep dive. And if you're serious about digital pathology, grab my free book at digitalpathologyplace.com. This is the best place to start your digital pathology journey. Thank you so much for listening, and I'll talk to you in the next episode.